What happens when the most destructive entities in the cosmos stop existing alone? What happens when these dark giants begin orbiting each other in the deep void? Most people picture a black hole as a solitary, isolated cosmic phantom. They imagine a single abyss wandering silently through deep space, swallowing everything. This classic image of a lone monster dominates textbooks and popular science films. But modern astrophysics reveals a far stranger and more turbulent reality out there. Black holes are actually rarely completely isolated in the vast cosmic expanse. Instead, they frequently exist in pairs, triplets, and dense gravitationally bound groups. Across the cold cosmic void, binary black holes perform complex, million-year orbital dances. In the centers of merging galaxies, supermassive black holes spiral toward inevitable union. These multi-black hole systems bend space and time in incredibly extreme, unique ways. They warp spacetime, create massive gravitational ripples, and distort passing starlight completely. How do these multiple void systems form without destroying each other instantly? What incredible phenomena occur when two light-devouring giants share the same space? Today, we step beyond single black holes to explore these intense, multiple systems. To understand multiple black holes, we must look at how star systems evolve. In our universe, a vast majority of massive stars are born in pairs. These sibling giant stars spend millions of years orbiting each other in harmony. They dance in a violent cosmic partnership, sharing gas and immense heat energy. As these giant stars exhaust their nuclear fuel, they undergo dramatic core collapse events. Supernova explosions shatter the local space, leaving behind two dense stellar remnants. When both massive stars collapse, they leave behind two stellar mass black holes. These twin remnants remain bound tightly by their mutual, inescapable gravitational pull. Alternatively, in dense globular star clusters housing millions of tightly packed stellar bodies, dynamic interactions and chaotic close encounters occur constantly between wandering objects. Single black holes gradually sink toward the dense cluster center over long eras. This migration happens due to a physical process known as gravitational mass segregation. As they crowd together, gravity forces them into tight, chaotic binary partnerships. These dark companions embark on a long orbital journey across millions of years. They siphon dust and gas from surrounding space, fueling their immense hunger. This material creates twin glowing accretion disks that brightly illuminate the dark void. Their intense mutual gravitational pull warps background starlight into intricate double-ringed lenses. They become ultimate cosmic dance partners, linked by the strongest gravitational bonds. While stellar mass binaries exist inside clusters, a far grander phenomenon occurs elsewhere. This immense process takes place directly at the hearts of massive galaxy centers. Nearly every large galaxy harbors a central supermassive black hole at its core. These monsters contain millions to billions of solar masses within their event horizons. Over cosmic timescales, Entire galaxies collide and merge due to mutual gravitational attraction. When two galaxies merge, their central supermassive black holes do not collide immediately.
Instead, they slowly sink toward the center of the newly merged galaxy system.
This gradual descent occurs through a subtle drag process called dynamical friction. As they plow through surrounding gas and star clusters, they lose orbital energy. This loss of energy takes place over many millions of turbulent years. Eventually, they become gravitationally bound to each other, forming a supermassive binary. These giant pairs can orbit each other at incredibly close stellar distances. Sometimes, their orbital distance is smaller than the span of our solar system. As they orbit, their massive gravity clears out all surrounding stars completely. This stellar eviction creates massive galactic core cavities devoid of glowing stars.
In rare instances, a third galaxy collision introduces another supermassive black hole.
This cosmic arrival creates a chaotic, unstable three-body dance of immense scale. The unpredictable gravity violently slingshots one massive hole far out into space. These cosmic triple systems represent the absolute limit of extreme gravitational interaction.
As binary black holes draw closer, a fascinating physical dilemma finally emerges. This cosmic mystery is famously known to astrophysicists as the final Parsec problem.
Gas and stars near the binary system are gradually ejected into outer space.
This ejection leaves the two massive black holes isolated in empty space.
Without surrounding matter to absorb their orbital energy, they cannot get closer.
The black holes struggle to close the final, agonizing gap between them. They can remain stuck orbiting each other for billions of years, empty-handed. This orbital lock occurs at a distance of roughly one single parsec. How do they ever manage to bridge this final gap and merge? The answer lies within the very fabric of space and time itself. They bridge this distance through the emission of powerful gravitational radiation waves. As two massive black holes orbit rapidly, they disturb the space-time grid. They continuously emit invisible ripples called gravitational waves across the cosmos. These cosmic ripples carry precious orbital energy away into deep, dark space. As energy drained into space-time waves, they enter a rapid death spiral. In their final moments, they revolve around each other hundreds of times.
This hyper-fast orbit occurs in the span of just one single second.
Their orbital speed approaches a significant fraction of the speed of light.
The surrounding space bends so severely that light trails form hypnotic rings.
These glowing Einstein rings create stunning optic illusions around the swirling pair. This final spiral creates an intense crescendo of pure space-time energy waves. This ultimate energy blast radiates across the entire length of our universe.
For centuries, observing multiple black holes was considered an impossible scientific task. This difficulty existed because black holes emit no visible light of their own. However, modern scientific breakthroughs have opened a completely new way of sensing.
We now have advanced tools to listen to the whispers of gravity. Advanced laser interferometers can detect the microscopic stretching of physical space.
This subtle stretching is caused directly by passing gravitational wave pulses. When two black holes merge far away, their final pulse passes directly through Earth. These signals allow scientists to calculate the exact masses of both black holes.
They can also determine the precise spin speeds of the merging cosmic giants.
Furthermore, space telescopes scanning X-ray wavelengths detect binary supermassive systems.
They identify these hidden pairs by carefully observing periodic stellar light dips. As one black hole passes in front of its companion's accretion disk,
it acts as an incredibly powerful, natural gravitational magnifying glass.
This magnification produces predictable X-ray pulses that reveal the hidden pair. Pulsar timing arrays use natural cosmic clocks to sense low-frequency gravitational hums.
This deep hum is created by thousands of supermassive binary black holes.
We are finally listening to the Cosmic Symphony, generated by multiple systems.
Multiple black hole systems challenge our fundamental understanding of physical laws. They transform our view of space from a vacuum into rippling fabric. From stellar twin systems to merging giants, they showcase gravity's ultimate power. Each binary detection brings us closer to solving how galaxies grow. The universe is far more crowded than early astronomy ever dared imagine.
Share your thoughts in the comment section below this cosmic exploration video.
Thank you for watching, and stay curious about the universe's ultimate mysteries.